So let me start with the brief introduction about the Reed-Solomon code. So in data communication, especially in digital communication, data can get corrupted during the transmissions, which caused by some reasons such as noise or crosstalk. So the Reed-Solomon codes are a group of error correcting codes that were introduced by Irving S. Reed and Gustav Solomon in 1960. It is one of the oldest, but it is still widely used because of the very well defined and several efficient algorithms which are now available under the public domain. So, where does it apply? Essentially, Reed-Solomon code correcting the error in storage devices including tape, CD, DVD, barcodes or QR codes. In wireless or mobile communication, in digital television or in high-speed modems. So guys, as you can see in the figures, the workflow of the Reed-Solomon code. The Reed-Solomon encoder basically takes a block of digital data and adds extra redundant bits. An error occurs during transmission or storage for a number of reasons. For example, noise or interference, scratches on a CD. The Reed-Solomon decoder processes each block and attempts to correct errors and recover the original data. The number and type of errors that can be corrected depends on the characteristics of the Reed-Solomon code.
Reed-Solomon code is a block code and it's shown in figure 1. Can be defined as RS and K. N is a block length. K is number of original message symbol. 2T is a number of parity digit. D is the minimum distance. What happened in encoder and decoder? Encoder take a K data symbol for each of the S bit and add parity symbol to make an N symbol code. Each of the S bit there is an NK parity symbol. At the decoder can correct up to T symbol that contain an error in a code word, where 2T is equal to N minus K. Reed-Solomon protected communication of a data transfer channel. At the transmitter end, the RS encoder encodes the input message into a code word and transmit the same through the channel. Noise and other channel disturbance can interrupt the code word and corrupt it. The corrupted code word reach at the end of the receiver, which is decoder, where it gets checked and receiver receive the corrected message. If the channel induced error is a greater than a decoder error correcting capacity, the decoding failure can occur. If the code word is a pass-on change, decoding failure are said to have occurred, and decoding failure, on the other hand, would result in a wrong message being issued at the output. The properties of a Reed-Solomon codes that make them especially well suited to the application where error occur in a burst. How many bits in a symbol are in error does not matter to the codes. If several bits in a symbol are correct, it's only count as a single error. Alternatively, the Reed-Solomon code is typically a bad choice if a data stream is not distinguished by the error burst or dropout, but by random single bit error. Number 2 is the natural size of a Reed-Solomon code block are not expected to use by a designer. A technique known as a shortening, with the generals a smaller code from a larger code of any desired duration. The commonly used 255251 code, for example, can be translated to 160128. and not transmitted. The same portion of the block is filled locally and binary 0 in the decoder. The third one is it is better for designer to use it as an encoding and decoding tools because of its ability to correct both burst, error and eraser.
So I will explain about encoding. So basically, what is encoding in Reed-Solomon code? Encoding in Reed-Solomon code is use of systematic encoding, which means that the parity of the block data does not change the message data. And then in systematic encoding is known as for polynomial form. Encoder of architecture. Encoder are built to be a feedback shift register, and you can see that in the figure 1. The data message block of 223 symbol passes sequentially as an input to the encoder. Once the last message symbol is loaded, the feedback register contains 32 parity check symbol. And then for the step of encoding, the first step is in the form of a polynomial, for example mx. The second step is mx polynomial with x n minus k to allow way for residual polynomial. And the third step is divide mx x n minus k by generator of polynomial gx to give rx or residual polynomial. Coding explanation. An information sequence is provided by the encoder and encoded block consisting of n equal to n minus 1 symbol each R form. The encoder also divides the information sequence into message block of k equal n minus 2t symbol. Each message block is equivalent to a message polynomial of degree k minus 1, denoted as mx. In systematic encoding, the encoded block is formed by simply appending 2t redundant symbol to the end of the k symbol long message block as shown as below. Since in Carlos field to M algebra plus and minus are the same, the code word actually equal the polynomial x 2tmx minus its remainder under division by gx. So it follows that cx is a multiple of gx. Since there is a total of 2mk different possible message, there are 2mk different valid code word at the encoder output. This set of 2mk code word of length n is called an nk block code.
Generator polynomial. A Reed-Solomon code word is generated using a special polynomial. All valid code words are exactly divisible by generator polynomial. Second, the general form of the generator polynomial is shown at the slide, and the code word is constructed using cx equal to gx multiplied by ix. Next, polynomials whose coefficients are Galois fifth element are broadly used in Reed-Solomon decoders. The often used operations associated with polynomials are first addition, second multiplication, third division, fourth computing remainder of polynomial division, and evaluation of polynomials. Decoding algorithm. Decoding is a process of transformation of received vector from communication channel onto sequence of information elements which were used to create code word. It may happen that received vector is not code word because code word was corrupted in communication channel. In this case, code can correct number of errors up to value of error correction capability. If decoder is not able to correct received vector and such situation can be recognized, then it is called decoder failure. If there occur so many errors that received vector is decoded onto different code word than original, then such situation is called decoder error. Next, a general architecture for decoding Reed-Solomon codes is shown in the following diagram. The received code word Rx in the original transmitted code word Cx plus errors. A Reed-Solomon decoder attempts to identify the position and magnitude of up to t error or 2t erasures and to correct the error or erasures. Next, in decoding algorithm has a error tapping order and cyclic decoding with multi-reading. First, error typing order decodes receive vector cyclically. It is used for systematic RS code with error correction capability of T. It consists of 4 parts. First is syndrome register, second buffer register, third unit which checks Hamming wave of syndrome, and lastly is control unit. For cyclic, decoding with multi-reading can be used to boost speed of cyclic decoding, which is finding remainder of division of received vector by code generator polynomial. This remainder should be of Hamming weight less or equal to error correction capability. Division of polynomials is not dependable from previous division, so this task can be split within threads. In decoding algorithm has a Peterson-Goriston-Ziller algorithm. Decoding with Peterson-Goriston-Ziller algorithm consists of 3 main steps. First is finding number of error, second finding position of error, and lastly is finding value of error. For finding number of error can be done by computation of determinant of matrix for V equals to T and then by checking whether matrix is invertible or not. If matrix is not invertible, then there is computed determinant of matrix where mu V equal to T1. The result is polynomial whose multiplicative inverse of root are position of errors. The syndrome value and error position are used to compute error value. Next, for finding position errors, Reed-Solomon can be treated as non-binary code, which means that code symbols are non-binary. During decoding binary codes, there is needed one information to correct error, which is error position. This error can be corrected by adding 1 to value on error position. For non-binary codes, this is a bit more complicated because except error position, there must be non-error value also. There are described algorithms for finding error position and error values, such as Berkeley-Macy algorithm, Sugiyama algorithm, and chain search. Lastly, finding value error used to find error value to determine error value. There is needed derivative of error locator polynomial, error evaluator polynomial, and error locator.
Implementation of the Reed-Solomon encoder and decoder. The first one is barcode format such as QR code. Individual code block may have more than 255 code word in a length. Because of that, more storage are used in a QR symbol. It is important to split up the message into several blocks so it will reduce the error for each block. The second one is data storage media such as DVD and CD. First one is audio CD error correcting. Code word obtained as a transmitted from C2 and then to C1. The C2 is used to correct single error and C1 is used to correct up for eraser. If at C2 detect no error, C2 will pass the information symbol to C1 with all eraser indication off. If otherwise, C2 will correct up the error. If C2 detect more than one error, all information will be set eraser flag, which means that they are all reliable. The second one is DVD error correcting. DVD tend to suffer from a combination of random and burst error. DVD needs the more efficient error correction system because the higher physical density means that more bits will be affected proportionally by any physical imperfection. FPGA area optimization in a space application. In digital communication channel prone to burst error, the best coding option will usually Reed-Solomon code. In the RS implementation, a linear feedback shift register LFSR was used. And LFSR was a shift register and feedback function. This function is used to shift the content of the LFSR around the register. It can be in a serial, parallel, conversion, or to delay bit stream. The last one is error control for system feedback. Reed-Solomon could allow the transmission of the information from receiver back to the transmitter for application instant, mobile data transmission system, and high reliability military communication system.
So, in a nutshell, after all of the discussions, we can say that Reed-Solomon codes were the first widely used codes that can correct multiple errors and it corrects bursts of errors to adjacent bits. The RS codes is based on a specialized area of mathematics known as Galois field or finite fields. This arithmetic operation must be done by a Reed-Solomon encoder or decoder. They do this by turning words made up of bits into sequences of elements of a finite field with Q elements, where Q is large and working in that finite field.